Hello everyone, this is a talk of paper minimum star partitions of simple polygons in polynomial time. This is a joint work with Mikko, Joachim, and Andre. I'm Hanwen. The problem we work on is a partitioning version of the famous art gallery problem. In the art gallery problem, we are seeking for a minimum number of guards to see the whole art gallery together. A region that can be seen by a single guard is called star-shaped. In this work, we are working on the partition version of this problem, seeking for a partition of the art gallery into minimum number of regions, so that every single region can be seen by a single guard inside this region. The figure shows a star-shaped region, and the red triangle marks where a guard can be. This is a fundamental problem in computational geometry, which has been opened for over 40 years. Besides theoretical interest, it can also be applied in some practical scenarios, including robot motion planning. In 2022, Abrahamson, Admashik, and Milzov showed that the art gallery problem for simple polygons is ETR complete, which is believed to be even harder than SAT. One might guess that the minimum star partition is a good approximation for the art gallery problem, but unfortunately, it can have a linear gap. In this figure, two guards are sufficient in the covering version. However, in the partitioning version, we have to break either the red piece or the blue piece, and the broken one has to use linear number of pieces. In 1983, O'Rourke and Shupwait showed that the minimum star partition is NP-hard for polygon with holes. But no exact algorithm is known up to our knowledge in the general case for simple polygons, even if any approximation algorithm with a sublinear approximation ratio. In 1985, Kell gave a polynomial time algorithm to find the minimum star partition for simple polygons that do not allow Steiner points. But sometimes Steiner points are crucial to reduce the number of regions. A Steiner point is a point that is a corner of some star-shaped region, but is not a corner of the input polygon. In this example, with the help of the Steiner point in the middle, we can partition the polygon into 4 pieces. However, if Steiner points are not allowed, we have to use linear number of guards, since some pieces has to be broken. In our paper, we give a polynomial time algorithm to find the minimum star partition of a simple polygon and answer the long-standing open problem confirmedly. Our key idea is to discretize the solution space by considering the extreme solutions that optimize some objective functions, and the optimality will provide some useful combinatorial properties as a reward. We first look at an example with a degenerate solution space. So here, the minimum star partition is unique. It's easy to see that the full partition is constructible by pen and ruler starting from the input polygon, which leads to a discrete space. Therefore, we are seeking for an objective function that guarantees this kind of constructibility. We formulate the objective to be the lexicographic order of the coordinates of the guards. In every partition that maximizes objective, each guard must be restricted by at least 2 half-planes, and the 2 half-planes represent where the guard is constructed from. We formulate the construction process in the following way. Starting from the input polygon, at each time, we can either construct a new guard from few existing Steiner points or corners of the input polygon, or construct a new crucial Steiner points from 2 guards and 2 concave corners of the input polygon. The construction process we define captures the 2 degenerate cases below. By geometric analysis, all crucial Steiner points have the same local structure, which we call tripod. A tripod is an interior point in the input polygon, and a sufficiently small disk around it is covered by exactly 3 pieces, and the 3 boundary edges connected to it are tight constraints to the corresponding guard from the same side, either clockwise or counterclockwise. Actually, tripod matches all the local structures of the degenerate case. We also observe that all the tripod in a specific partition forms a tree structure. For a specific partition, if we only look at the boundary edges around the tripod, then all the faces forms a tree structure if the tripods are treated as a degenerate face. We can choose the face that shares a specific boundary edge with the input polygon to be the root. So for example, here F4 is the root face, and then we can make the tree rooted like this. Note that we can easily distinguish the parent side of a tripod locally without looking at the whole partition. Although the space for guards is discrete now, there can be super exponentially many points. The next step is to reduce the size to a polynomial. Therefore, we'd like to determine the tripods one by one in the topological order of the tripod tree. In our full paper, we prove that the construction can also follow the topological order of the tripod tree, but we need to use a slightly modified objective function in the same flavor. We achieve this goal by a process called greedy choice. Suppose we have a partition that has a tripod, and we have another way to partition the similar yellow region. Then we can convert the original partition into a new one without this tripod. Note that this kind of conversion is applicable as long as this angle increases. Therefore, a tripod is not necessary unless it gives the most freedom for the future. So we only need to care about the best tripod for each place. Since a place for a tripod to exist can be determined by the 3 concave corners involved. So after applying the greedy choice, the number of tripods in consideration is reduced to a polynomial. Then the space for guards in consideration is also reduced to a polynomial. Now we are going to show our dynamic programming algorithm. From previous steps, we force all the guards to be in a polynomial-sized set. And using similar techniques, we can also force all the Steiner points to be in a polynomial-sized set. Another observation suggests that the dual graph of an optimal star partition must be outerplanar. Combining these 3 properties, we devise a dynamic programming algorithm from the existence of simple separators. The outerplanarity suggests that 2 neighboring star-shaped regions is enough to disconnect the polygon. A cut vertex in the dual graph corresponds to a short separator in the partition, consisting of 2 segments that connect the guard of this piece to 2 points on the boundary. A cut of 2 neighboring vertices in the dual graph corresponds to a long separator in the partition, consisting of 4 segments that connect the guard of each piece to a point on the boundary, and then connects them through a point on the shared boundary. As promised, every point involved is chosen from a polynomial-sized set, so we only have polynomially many separators. We show that it is sufficient to find an optimal partition with the following types of transitions. Case 0 initializes 2 types of trivial separators. Case 1 shows how to merge 2 short separators if the guard is the same. Case 2 shows how to deal with a degenerate long separator, corresponds to a degenerate cut of 2 vertices in the dual graph. Case 3 shows how to merge 2 short separators into a long one. Case 4 shows how to expand a long separator. And case 5 shows how to merge long separators, corresponds to a triangle in the dual graph. The last issue is to decouple the process of determining the best tripod and determining the optimal star partition for each subpolygon. We resolve this issue by a two-phases algorithm. To determine the best tripod, we first determine all possible descendant tripods recursively. After that, we can compute the minimum star partition for every subpolygon in the descendant faces to the tripod. Then, we can determine the best tripod by enumerating the two guards that's used to construct this tripod. Although our algorithm runs in polynomial time, it's still far from use. The natural question is to find a faster algorithm for this problem that can use in practice. We believe that using similar techniques, one can design a polynomial time algorithm for some other polygon decomposition problems. For example, partition a simple polygon into minimum number of triangles. Thanks for your attention.